show that cosine of x equals the sum of its Maclaurin series. We haven't actually shown this yet. And okay, so the upshot of all that discussion above is that if we can show, for cosine of x, if we can show Rn goes to 0, Rn of x goes to 0, then that shows that the Maclaurin series we came up with for cosine of x does in fact converge to cosine of x. Okay, so if you think about it, Rn of x, the generic formula, was the n plus first derivative evaluated at some value c, we don't know what it was, over n plus 1 factorial times x minus a to the n plus 1. Now, for cosine, a was 0. For our Maclaurin series, a equals 0, right? Okay, remember when we went about taking several derivatives of cosine to come up with that series yesterday? Okay, when you take a derivative or a higher level derivative of cosine, it's either going to be sine or cosine, right? And we have a bound on sine and cosine. We have bounds on it. What does it lie between?
-1 and 1, right?
Both sine and cosine lie between -1 and 1. So these are derivatives starting with cosine, right? So whatever this is between -1 and 1. And being able to bound that thing is going to allow us to show that it goes to 0. Okay, now I'm going to take the absolute value of it. So the absolute value then, so that I get everything positive, the absolute value, and this is with regard to cosine of x, right? To the remainder for the Maclaurin series for cosine of x, that is. The absolute value of that thing is definitely going to be bigger than 0. So I'm talking about, you know, this thing up here. The absolute value of that thing is definitely going to be bigger than 0, but I claim it's going to be less than or equal to, I'm just going to replace the n plus first derivative evaluated at c, I'm going to replace that with 1. If I replace that numerator with 1, I know that that's going to be bigger than Rn of x, absolute value. So I replace that whole thing with 1. Okay, that stays the same. Now I did, so this is, since this is 0 right here, it's really x to the n plus 1. But I did take absolute value, so I got to put that somewhere. Right? I took the absolute value of this whole thing, but the only thing that's possibly going to be negative is x. So I'm putting the absolute value around that x to the n plus 1. Don't worry, I promise we're almost done. Any questions on how I got that?
Can you just say the part about the bounding? It's not about bounding.
Okay.
I know that it's between -1 and 1, but about the derivative part.
Right, when you take the derivative of cosine of x, right? And so the n plus first derivative of cosine, let's put it this way. I'm glad you mentioned that. The n plus first derivative of cosine evaluated at, doesn't matter what c is. It's going to be either sine or cosine, right? We don't know what n is, so we don't know which one it is. But both of them are bounded between -1 and 1. And so what I'm saying is, hey, if I take the absolute value of Rn of x, I know, since that numerator, the n plus first derivative, since that numerator is between -1 and 1, and if I take the absolute value, I can get it between 0 and 1, I know that this Rn of x that I have up here, if I take the absolute value of it, will be less than this guy, because all I'm really doing, besides taking absolute value, is replacing the n plus first derivative with 1. It bounds it.
So we probably could do this as easy with like e to the x or something.
Well, with e to the x, the trick is to realize that it's an increasing function. So if you restrict what you're looking at to a finite interval, so if you know a is like 1, so you could restrict your interval to be between 0.5 and 1.5 or something like that. And then you know that e to the x then on that interval from 0.5 to 1.5 e to the x will be less than e to the 1.5, less than or equal to e to the 1.5, the endpoint of that interval, because it's an increasing function. So there are tricks you can do to get the boundary, in other words. This one is particularly easy, but there are other tricks you can use. Okay, so we did that. Now, look, notice what I wrote down here ahead of time to save a little bit of time. There was a homework problem in 11.8 where you showed, I don't remember which number it was, but you showed that this guy, remember 11.8 was the ratio test, all those? You use the ratio test to show this guy, sum x to the n over n factorial, is absolutely convergent, right? So the sum of the absolute values converge. Oh, well, if this guy's convergent, the an, this guy has to converge to 0. In order for a series to converge, the an, the thing that the part that comes after the sigma notation, has to converge to 0. So we have that result. And since it converges absolutely, you could throw in that. Absolute values around the whole thing, which is equivalent to that. Oh, but isn't this, it doesn't matter if it's n or n plus 1. So don't we know this guy on the right here converges to 0? Yeah. So this guy converges to 0. I'm being very informal here. I'm not writing it out like if I wanted to put it in a book, but I just want to get the idea across. Converges to 0, you know, by this result. So, oh, if that guy converges to 0, and Rn of x is less than that guy, absolute value-wise, is less than that and a bigger than 0, what can we say about absolute value of Rn of x? It converges to 0, which means Rn of x converges to 0. We have a theorem that says if the absolute value of a sequence converges to 0, you think of Rn of x as a sequence, not a series. If the absolute value of Rn of x converges to 0, then Rn of x converges to 0, right? Okay, so of course 0 converges to 0, so Rn of x, absolute value, is squeezed down to 0. So Rn of x, absolute value, converges to 0 by squeeze theorem. Which means Rn of x converges to 0. And so cosine of x is equal to the sum of its Maclaurin series. Luckily, you won't have to do much of or any of this in the homework. But it wouldn't be complete if I didn't mention it. And if you take you computer scientists in here, you're going to have to take a class called numerical analysis eventually, most likely. When I took it, this result was in the first week of class. Okay? It's an important result.